was why does the amplitude variation in a modulation scheme matter? Some of the modulation scheme results in constant power. For example, QPSK has constant power regardless of which symbol you're actually transmitting, while others, like the 16QAM, will have a different amplitude depending on the symbol you're transmitting. So why does this matter? So first of all, there are ways you can quantify this. So you can clearly see here there is something called the crest factor that we can define. It's a very simple idea. You're comparing the peak signal, which you can see here, to the RMS value of your signal. So some people will quantify this variation with a crest factor. Others, and you have a homework on that, will actually quantify this with a peak to average power ratio, which is essentially the peak power you're transmitting versus the average power you're transmitting. And I find this a little bit more intuitive because this is really what we care about, is the power that we're transmitting. But if you do the little math here, you will find out that this is nothing else but the crest factor square. So nevertheless, this is where the math ends, and this is where I think our discussion begins, is why does it matter to think about that? So in order to really realize that we really have to think about a transmitter in a most simple way. So the transmitter usually at the end of its transmitter chain will include a power amplifier, and this power amplifier will feed the signal to an antenna, and this antenna will basically emit the wave that's supposed to go into space. So the key feature here is that this power amplifier will basically get at its input something in the order of milliwatts and will have to transmit something in the order of watts. So there's significant amplification that is required, and for that reason this power amplifier actually consumes quite a bit of power. In fact, this is the most power hungry element in a transmitter chain. So it's not uncommon to design systems where your power amplifier at the end will consume 80 to even 90% of your total power for your RF transmitter, because this guy has to spend a lot of power to actually transmit watts. Now, where does it gain this power is clearly from the DC. And so essentially what I mentioned also last time, the power amplifier takes DC power and transfers it into RF. But it does this as a cost. And that cost is what we call efficiency. So the efficiency is not 100%. When you take DC and transfer it to RF, you're going to pay a penalty. And not only is it not 100%, but it actually depends on how much power you're transmitting. In fact, when you design an amplifier, if you were to plot efficiency as a function of the amount of power that you are transmitting, the line is going to look something like this, right? It will always depend on the actual design that you have, but it will be relatively low for low powers, and it will actually improve to something higher. So it is actually to our advantage to always transmit here. So we always want to basically utilize this region because that will basically save the most amount of power in your receiver. But the problem is that when you're transmitting at a very high power, then your linearity suffers. So you basically have this fundamental trade-off that essentially says that you want high efficiency, well, you might have to get bad linearity. So bad linearity means that you're altering your spectrum, right? You're starting with one frequency here, and you end up with basically a mess at the end, right? So not only there are actually regulations that will tell you that you can't pollute the spectrum by having too many unwanted harmonics, but you also make the signal to be very different than what you intended to be, which basically makes the decoder's job very, very hard. So the worst thing you can do is basically choose a waveform that actually suffers the worst from bad linearity, and these are actually the waveforms that don't have constant envelope. And so as much as possible, we try to pick waveforms that have constant envelope. Of course, sometimes that's not possible, but if you have the chance to design a system with a constant envelope scheme, then that means that you make that choice early on, you make the PA designer's job far, far easier. So that's one of the things that I will keep pointing out in this course, is that these type of links exist all the time, and that's why it makes sense to look at the system from a system perspective and not just focusing on a single device.